Right now, as you listen to this, something unprecedented is happening in our solar system. Ever since 3I Atlas was discovered in July, things have been getting progressively weirder up there. This ancient interstellar visitor has baffled astronomers from day one. But its impossible chemistry and green glow aren't the strangest part anymore. The strangest part is what has been following in its wake. Our usually predictable cosmic neighborhood has turned into a busy highway of converging objects with clustering patterns that defy probability. From a swarm of 7 comets arriving together to a fresh wave of asteroids flying past Earth, what we are seeing in the night sky is anything but normal. And now, astronomers have no choice but to start asking, what is 3I Atlas really doing to our solar system? Stay with me on this late-night exploration as we uncover whether we are witnessing the galaxy's greatest coincidence or something far more profound. Mid-September 2025 was supposed to be quiet. It was just another month of routine cosmic traffic, the kind astronomers catalog with mechanical precision before moving on to their next observation. But the universe had other plans. What unfolded in those crisp autumn weeks was something entirely different, a celestial parade that left scientists scrambling to their telescopes. The headliner arrived first, Asteroid 2025 FA22, a mountain-sized chunk of rock measuring somewhere between 130 and 290 meters across. On September 18th, it swept past Earth at just over 2 lunar distances, roughly 835,000 kilometers away. It was close enough to make headlines, yet far enough to let us sleep soundly. But here is where the story gets interesting. FA22 did not come alone. This was not a typical lone wolf asteroid making its scheduled appearance. Instead, it felt more like opening night at a cosmic theater, with multiple performers taking the stage in rapid succession. Small near-Earth object 2025 RJ2 had already made its entrance 3 days earlier, on September 15th, buzzing past at just 0.78 lunar distances, a mere 300,000 kilometers from our doorstep. In astronomical terms, that is practically a handshake. But these were not isolated incidents. Throughout that same week, dozens of additional sub-lunar distance visitors painted their trajectories across our local neighborhood. Each one was cataloged and tracked by the global network of space surveillance systems. It was typical traffic by the numbers. Yet something about the clustering felt different. The timing seemed almost choreographed, as if these ancient wanderers had coordinated their arrival for maximum dramatic effect. Then came the supporting cast. Comet C2025-R2, discovered by the Swan instrument aboard the SOHO spacecraft on September 11th, began brightening toward naked-eye visibility near the constellation Virgo. Its tail stretched across the evening sky like a cosmic brushstroke, visible to anyone who knew where to look as twilight surrendered to darkness. Meanwhile, lurking in the background of every astronomical news report was another familiar face, Apophis, officially designated 99942 Apophis. This is the 400-meter-wide asteroid that once topped every planetary defense worry list. It is scheduled for an uncomfortably close encounter with Earth on April 13, 2029. That flyby will bring Apophis within 32,000 kilometers of our planet's surface, closer than our geostationary satellites. But the real star of this celestial show was still waiting in the wings. Hidden among the routine discovery announcements was something unprecedented. 3I Atlas, also known as C2025-N1. Discovered on July 1, 2025, by the Atlas survey team in Chile, this object was different from everything else crowding our telescopes that September. It was not just another asteroid or comet from our local solar system family. This was something far more exotic, an interstellar visitor. It was only the third ever confirmed, carrying chemical signatures that would challenge everything we thought we knew about planetary formation. The Atlas team had initially spotted it as just another fuzzy dot moving against the star field. But as follow-up observations refined its trajectory, the mathematics told an extraordinary story. This object was traveling on a hyperbolic orbit, meaning it possessed more than enough velocity to escape our sun's gravitational embrace entirely. It had come from somewhere else, another star system, perhaps light years away. After its brief encounter with our solar neighborhood, it would continue on into the cosmic dark, never to return. What made 3I Atlas even more remarkable was its timing. Perihelion was scheduled for late October 2025, just weeks after the September asteroid parade. Then, like a performer exiting stage left, it would vanish into the solar glare, hidden by our star's overwhelming brightness. But patience would be rewarded. In early December, as Earth's orbital motion carried us to a better viewing angle, three-eyed St. Atlas would re-emerge from behind the sun's curtain, offering telescopes their best opportunity to study an authentic piece of interstellar real estate. The observing window was perfect. At closest approach in December, the object would still be 1.8 astronomical units away, roughly 270 million kilometers from Earth. Far enough to pose zero threat, yet close enough for detailed spectroscopic analysis by our most powerful instruments. It was as if the universe had delivered a carefully packaged sample from another star system directly to our astronomical doorstep. But why now? Why this sudden surge of cosmic activity clustering around the same few weeks? Better surveys certainly played a role. The Vera C. Rubin Observatory had just captured its first light images in June 2025, netting thousands of new asteroid detections in approximately 10 hours of operation. More eyes were scanning the sky with greater sensitivity than ever before, revealing the true population density of our solar system's small body constituency. Yet, the timing felt too convenient, too orchestrated to dismiss as mere observational bias. Was there something special about September 2025? Some gravitational confluence or seasonal alignment that had drawn these objects into convergence? Or were we witnessing the first act of something larger, a cosmic drama playing out on timescales far beyond human perception? The mood among astronomers was not fear, but urgent curiosity. The September surge had awakened something in the collective scientific consciousness. The recognition that our solar system was far more active, far more connected to the broader galaxy than we had previously imagined. We were witnessing the opening act of humanity's transition from a single-planet species to active participants in galactic-scale phenomena. The mathematics of cosmic collision are unforgiving. When asteroid 2025 FA22 swept past Earth on September 18th, it carried with it the kinetic energy equivalent of roughly 100 megatons of TNT. To put that in perspective, that is approximately 2,000 times more powerful than the bomb that leveled Hiroshima, all concentrated in a single rocky projectile. But energy is only part of the story. What matters most is how that energy gets delivered to our planet's surface. That depends entirely on a complex dance of physics involving atmospheric entry angle, object composition, and sheer cosmic luck. The difference between a regional catastrophe and a global extinction event often comes down to factors as simple as whether the incoming object is made of solid iron or loose gravel, and whether it explodes in the air or punches through to the ground. FA22's approach velocity of approximately 10.8 kilometers per second was typical for near-Earth objects. At that speed, atmospheric entry would have been spectacularly violent. The object would have begun glowing like a second sun while still hundreds of kilometers above the surface. For a stony asteroid in FA-22's size range, the most likely scenario would have been an airburst, a complete atmospheric explosion occurring somewhere between 5 and 15 kilometers above the surface. This is what happened at Tunguska, Siberia in 1908, when an estimated 3 to 15 megaton air burst flattened over 2,000 square kilometers of forest without ever creating a crater. The FA-22 scenario would have been significantly more powerful. Imagine standing 200 kilometers away from ground zero on a clear morning. First would come the light, a flash brighter than the sun, visible even in broad daylight, burning retinas and igniting vegetation across hundreds of square kilometers. The thermal pulse would last several seconds, long enough to cause third-degree burns to exposed skin at distances exceeding 100 kilometers. Then would come the sound. The shock wave from a 100 megaton airburst would shatter windows across an area the size of a small country. The overpressure wave would flatten most residential buildings within 50 kilometers of ground zero and cause significant structural damage out to distances approaching 150 kilometers. But what if FA-22 had been made of denser material or arrived at a shallower angle that allowed it to penetrate deeper into the atmosphere before fragmenting? The crater scenario presents an entirely different kind of devastation. Using established impact modeling programs, we can estimate that a 200-meter iron asteroid striking at 10 kilometers per second would excavate a crater approximately 3 kilometers in diameter and 500 meters deep. The immediate effects would be apocalyptic for anyone within visual range. The impact would vaporize the asteroid and an equivalent mass of target rock, launching millions of tons of superheated debris on ballistic trajectories. Yet, perhaps the most terrifying scenario would be an ocean impact. Over 70% of Earth's surface is covered by water, making this statistically the most likely outcome for any randomly arriving asteroid. When cosmic projectiles hit the ocean, they create tsunamis. Even a 250-meter asteroid striking deep ocean would produce initial wave heights exceeding 100 meters at the impact site. These waves would propagate outward at jet aircraft speeds, carrying enough energy to remain dangerous across entire ocean basins. A FA-22-sized impact in the mid-Atlantic could potentially send 10-meter waves crashing into coastal cities from Boston to Barcelona within hours of impact. The regional versus global impact question is crucial for understanding the true threat posed by city-killer-sized asteroids. An FA-22 impact would certainly cause regional devastation, potentially affecting millions of people, but it would be unlikely to trigger global climate effects or threaten human civilization as a whole. That level of destruction requires much larger impactors, objects in the kilometer-plus size range that strike perhaps once every few 100,000 years. The FA-22 scenario serves as a sobering reminder that we live on a planet embedded in a shooting gallery of cosmic debris. Most of it is harmless, but occasionally something larger slips through the gaps in our detection network. The good news is that we are getting better at this cosmic neighborhood watch. New survey telescopes are coming online with unprecedented capability to detect and track potentially hazardous objects, while space-based infrared observatories will soon close the sunward detection gap that allowed the Chelyabinsk object to arrive unannounced in 2013. While asteroid FA-22 captured headlines with its close approach, another celestial performer was quietly preparing for its debut in the evening sky. Comet C-2025 or R2, discovered by the Solar Wind Anisotropes (SWAN) instrument aboard the SOHO spacecraft, was rapidly brightening toward naked-eye visibility as it fell inward toward the sun's position. Unlike the predictable, well-mapped trajectory of FA-22, this comet represented something far more volatile and unpredictable. Swan's discovery of the comet highlighted one of the most elegant aspects of modern space-based astronomy. The instrument was not designed to hunt comets. Its primary mission involves mapping hydrogen emissions from solar-wind interactions. But when comets begin their final approach toward the Sun, they start releasing hydrogen-rich water vapor in quantities detectable from millions of kilometers away. Swan essentially stumbles across new comets by watching for their hydrogen signatures erupting against the background of interplanetary space. By mid-September, C-2025 R2 had brightened to approximately 6th magnitude, hovering right at the threshold of naked eye visibility under dark rural skies. Amateur astronomers began reporting sightings near the constellation Virgo. The comet's tail was growing longer and more structured as solar heating drove volatile ices to sublimate from its nucleus, creating the classic coma and tail structure. But comets are notoriously fragile creatures. Unlike the solid rock and metal construction of asteroids, comets are essentially dirty snowballs. Loose aggregations of ice, dust, and organic compounds held together by weak gravitational forces. As they approach the Sun, the same heating that creates their spectacular tails can also tear them apart entirely. The physics behind comet activation involves a complex interplay of sublimation temperatures and solar heating. As these volatile materials transition directly from solid to vapor, they create jets of gas that can dramatically alter a comet's trajectory through non-gravitational forces. This makes comet orbits notoriously difficult to predict with high precision. Meanwhile, another cosmic celebrity was preparing for its own moment in the spotlight. Asteroid 99942. Apophis continues its inexorable approach toward the closest asteroid encounter in recorded human history. The flyby will bring it closer than our geostationary communication satellites, close enough to appear as a bright, fast-moving star, visible to the naked eye. What makes the Apophis encounter scientifically fascinating is that we know with absolute certainty it poses no impact risk for at least the next century. Radar observations and optical tracking have refined its orbit to extraordinary precision. This allows scientists to focus entirely on the remarkable opportunity to study a large asteroid during an extremely close approach. The gravitational effects of Earth's pull during the flyby will be profound and permanent. Apophis will experience tidal forces strong enough to alter its rotation rate and modify its surface features. The timing of Apophis's approach, coming just 3.5 years after the September 2025 surge, raises intriguing questions about whether we are entering a period of increased near-Earth object activity. Statistically speaking, close asteroid approaches follow no particular schedule. Yet, the clustering of significant encounters within such a short time frame seems to challenge the notion of purely random distribution. Part of this apparent increase stems from observational bias. The completion of major asteroid surveys over the past 2 decades has dramatically improved our ability to detect and track potentially hazardous objects. The Vera C. Rubin Observatory represents another quantum leap in survey capability. Its enormous field of view and sensitive detectors will rescan the entire accessible sky every few nights, providing unprecedented cadence for discovering new objects and monitoring known ones. The diversity of small body types, asteroids, rocky metallic, comets, volatile rich, and meteors, atmospheric burnup phenomenon, reflects the complex history of our solar system's formation and evolution. The asteroid belt contains remnants that never successfully assembled into a planet, while comets preserve samples of the primitive ices and organics from the outer reaches of the early solar nebula. As autumn 2025 progressed, the cosmic stage was set for even more remarkable revelations. The September surge of familiar solar system objects was about to be overshadowed by a visitor from another star system entirely. On July 1st, 2025, a routine automated sky survey captured something extraordinary, disguised as an unremarkable dot of light. The Atlas Telescope Array photographed thousands of such objects, but this particular dot would soon rewrite our understanding of what travels between the stars. It was during the routine astrometric follow-up that astronomers realized they were dealing with something unprecedented. The mathematics were unmistakable. Its orbital eccentricity exceeded unity. In celestial mechanics, this is the signature of a hyperbolic trajectory, an orbit carrying more than enough velocity to escape the sun's gravitational influence entirely. This object was not bound to our solar system. It was just passing through. 3I Atlas became only the third confirmed interstellar visitor in human history, following the mysterious cigar-shaped object 1I Oumuamua in 2017 and Comet 2I Borisov in 2019. But unlike those previous visitors, 3I Atlas arrived with perfect timing for extensive observation. Its trajectory would carry it to perihelion, closest approach to the Sun, on approximately October 30th, 2025, followed by its closest approach to Earth in December, at a distance of roughly 1.8 astronomical units. The object's trajectory was only the beginning of its mysteries. As observational data accumulated, 3I Atlas began displaying characteristics that challenged assumptions about both interstellar space and comet behavior. Size estimates from Hubble Space Telescope observations suggested an upper limit of approximately 5.6 kilometers for the nucleus, placing it in the intermediate range between typical comet nuclei and small asteroids. What truly set 3I Atlas apart was its unmistakably cometary behavior. Unlike 1I Oumuamua, which showed no visible coma or tail, despite its puzzling non-gravitational acceleration, 3I Atlas developed a classic cometary appearance as it approached the Sun's position. By September, ground-based telescopes were resolving a substantial coma, the cloud of dust and gas surrounding the nucleus, along with the beginnings of what would become an impressive tail structure. This cometary activity provided the first clues to the object's truly alien chemistry. When the James Webb Space Telescope, JWST, turned its infrared spectrographs toward 3I Atlas in late summer 2025, the results were unlike anything seen in solar system comets. The object's coma showed an unusually high ratio of carbon dioxide, CO2, to water vapor, H2O, among the highest ever measured in a comet. The extreme CO2 dominance in 3I Atlas suggests formation in the frigid outer regions of its parent planetary system, far beyond where most solar system comets originate. Either this object condensed from a protoplanetary disk that was unusually rich in carbon dioxide, or it formed so far from its parent star that water ice never had a chance to accumulate in significant quantities. But the chemical anomalies did not stop with carbon dioxide. Spectroscopic observations from the Very Large Telescope in Chile revealed another puzzling feature: prominent nickel emission lines with surprisingly weak iron signatures. In typical solar system comets, iron and nickel occur in roughly solar proportions. The apparent depletion of iron relative to nickel in 3I Atlas hints at chemical processing or formation conditions unlike anything in our local cosmic neighborhood. As autumn progressed, 3I Atlas continued its approach toward perihelion, and its tail structure became increasingly complex and visually spectacular. The object was literally coming alive under solar heating after potentially billions of years in the cold emptiness between stars. Preliminary kinematic modeling suggested that 3I Atlas might be extraordinarily old, possibly more than 7 billion years. If recent calculations linking it to the galaxy's thick disk population proved correct, this would make it older than our entire solar system, a wanderer that had been drifting through interstellar space since before Earth existed. The September 2025 surge served as an uncomfortable reminder of just how precarious our planetary defense capabilities remain. Despite decades of technological advancement and international cooperation, while we successfully tracked and characterized every significant object that approached Earth during those eventful weeks, the clustering of encounters highlighted critical gaps that could prove catastrophic. Consider the fundamental challenge of detection geometry. The vast majority of our asteroid hunting telescopes are ground-based facilities that can only observe objects when they are sufficiently separated from the sun in our sky. This creates a massive blind spot in the direction of our nearest star, precisely the approach corridor that delivered the Chelyabinsk impactor, completely undetected in 2013. An asteroid approaching from the sunward direction remains effectively invisible until the final hours or minutes before atmospheric entry. This sunward blind spot represents one of the most significant vulnerabilities in our current planetary defense architecture. Ground-based surveys have made remarkable progress in cataloging near-Earth objects, but they remain fundamentally limited by the laws of optics and orbital mechanics. The solution involves moving detection systems into space. NASA's Near-Earth Object Surveyor mission, scheduled for launch in September 2027, will deploy an infrared space telescope specifically designed to hunt asteroids from a position trailing Earth in our orbit around the Sun. From this vantage point, NEO Surveyor will be able to detect objects approaching from directions that remain invisible to ground-based observatories. But detection is meaningless without the ability to actually do something about incoming threats. This is where NASA's Double Asteroid Redirection Test, DART mission, has provided invaluable real-world validation of kinetic deflection technology. DART's impact with asteroid Dimorphos successfully altered the small asteroid's orbital period by 32 minutes, far exceeding the required minimum change. More importantly, detailed analysis of the impact revealed that the momentum transfer efficiency was nearly 4 times more effective than predicted by simple momentum conservation. This enhancement factor results from the ejection of debris following impact, which acts like a rocket exhaust to amplify the deflection effect. Understanding this, physics is crucial for designing future deflection missions. The key insight from planetary defense research is that all of these techniques require substantial lead time to be effective. A gentle nudge applied years in advance can eliminate the need for desperate last-minute measures. This is why early detection is so critical. The International Asteroid Warning Network, IAWN, conducted what amounted to a live exercise during FA-22's approach. The rapid international sharing of observational data allowed quick refinement of FA-22's orbit and prompt removal from risk assessment lists once the threat was ruled out. However, the exercise also highlighted critical gaps. Long-period comets arriving from the outer solar system can still appear with relatively little warning. Perhaps most concerning are the city-killer-sized objects in the 100 to 300 meter range. Large enough to cause regional devastation, but small enough to remain difficult to detect until they are very close to Earth. The inventory of these smaller, potentially hazardous asteroids remains incomplete. The human brain is exquisitely designed to detect patterns, even when none exist. This evolutionary adaptation can lead us astray in the context of astronomical phenomena, finding connections and conspiracies in the random noise of cosmic events. Yet sometimes the patterns are real. Consider the timeline. Asteroid 2025, FA22 sweeps past Earth. Days later, smaller object 2025 RJ2 passes even closer. Throughout the same week, multiple additional near-Earth objects thread their way through our local neighborhood. Comet C2025 R2 brightens toward naked eye visibility. And, lurking in the background, interstellar visitor 3I Atlas approaches its October perihelion after a journey that may have lasted billions of years. The clustering of these events within such a narrow temporal window begins to challenge simple explanations based on cosmic coincidence. One speculative thread involves gravitational shepherding, the possibility that 3I Atlas's passage through the inner solar system could somehow influence the trajectories of smaller objects. However, the physics argue strongly against this scenario. Even at its maximum estimated size of approximately 6 kilometers, 3I Atlas carries insufficient mass to gravitationally influence objects at distances of millions of kilometers. Newton's inverse square law means that gravitational effects fall off rapidly with distance, becoming negligible at the scales involved in the September encounters. Moreover, the orbital elements of the various September visitors show no evidence of common origin or shared dynamical history. A more plausible explanation for the apparent clustering involves observational bias and detection cadence effects. The Vera C. Rubin Observatory had just achieved first light in June 2025, dramatically expanding our ability to detect and track small near-Earth objects. Improved survey coverage naturally leads to more discoveries, creating the impression of increased activity even when the underlying population remains constant. The psychological phenomenon of apophenia, the tendency to perceive meaningful patterns in random information, may also be influencing our interpretation. Once the first few close approaches were reported, both astronomers and the public became hyper-aware of subsequent discoveries. Objects that might have passed unnoticed during a quieter news cycle suddenly received front-page treatment, creating a feedback loop that amplified the perception of unusual activity. Furthermore, the fragmentation fantasy, the idea that FA22 and other near-Earth objects are fragments of the interstellar visitor, faces insurmountable problems. True fragments from 3I Atlas would retain hyperbolic trajectories and interstellar chemistry similar to the parent object. The September asteroids display neither characteristic. Their elliptical orbits and typical carbonaceous or silicate compositions indicate conventional solar system origins with no connection to interstellar material. Perhaps the most mundane explanation is also the most likely. We are witnessing the statistical equivalent of multiple lightning strikes, improbable individual events that occasionally cluster together through pure chance. The universe contains no obligation to distribute cosmic encounters evenly across human timescales. However, the discovery of 3I Atlas, with its trajectory precisely timed to reach maximum visibility just as near-Earth object activity peaked, remains a remarkable coincidence that stretches the limits of statistical probability. As 3I Atlas continued its approach toward its October perihelion, telescopes around the world began documenting behaviors that challenged fundamental assumptions about comet physics and interstellar chemistry. What had initially appeared to be a relatively straightforward case was revealing layers of complexity that seemed to violate established patterns of how such objects should behave. The most striking anomaly emerged from JWST observations. A coma composition dominated by carbon dioxide to an unprecedented degree, with CO2 to H2O ratios among the highest ever measured in any comet. This was not just unusual, it was borderline impossible, according to conventional models of comet formation and evolution. The extreme carbon dioxide dominance suggests either formation in the frigid outer regions of a planetary system, much larger or colder than our own, or subsequent processing that selectively depleted water while preserving CO2. The chemical anomalies did not stop with carbon dioxide dominance. Spectroscopic observations revealed prominent emission lines from nickel atoms, with surprisingly weak corresponding signatures from iron. This represents a significant departure from typical solar system compositions, where iron and nickel occur in roughly solar proportions. The apparent depletion of iron relative to nickel in 3I Atlas raises fundamental questions about its formation environment or subsequent evolution. It could reflect either differential processing of metallic components during its interstellar journey or formation in a stellar environment with non-solar elemental abundances. As summer turned to autumn, 3I Atlas's tail structure became increasingly complex and visually spectacular. Ground-based observations documented multiple tail components with different orientations, colors, and apparent particle sizes, suggesting ongoing activation of different volatile reservoirs across various regions of the nucleus. Polarimetry measurements suggested dust grains with unusual size distributions or optical properties compared to typical solar system comets. One particularly intriguing aspect of 3I Atlas's behavior involved apparent episodic brightenings that seemed to occur independently of its distance from the Sun. Most comets follow predictable brightening curves, but 3I Atlas displayed periodic flare-ups that suggested more complex internal processes. These outbursts might result from the sudden exposure of fresh, volatile-rich material as surface crusts are stripped away by solar heating, or they could reflect internal structural changes as 3I Atlas adapted to solar heating after billions of years in the cold emptiness of interstellar space. The rotational behavior also appeared anomalous. Photometric observations, designed to measure brightness variations, revealed either an unusually long rotation period or a complex tumbling motion that made period determination difficult. This might indicate structural modifications during its interstellar journey, or simply reflect the original angular momentum state from whatever event ejected it from its parent system. The most unsettling aspect of 3I Atlas's behavior was how normal it appeared in some respects, while being completely unprecedented in others. The basic physics of coma formation and volatile sublimation followed well-understood principles. Yet, the specific chemical signatures, temporal evolution, and structural properties seem to violate every expectation based on decades of comet research. This combination of familiar and alien characteristics suggested that 3I Atlas represented something genuinely new in astronomical experience. In the age of social media, it was perhaps inevitable that 3I Atlas would eventually face the question that has haunted every unusual astronomical discovery. Could this be evidence of extraterrestrial intelligence? The object's unprecedented chemistry, complex behaviors, and remarkably convenient timing for observation fueled speculation. The speculation began innocently enough in academic circles where researchers noted similarities between 3I Atlas and 1I, Oumuamua, which had sparked debates about possible artificial origins in 2017. Both were interstellar visitors, both displayed unusual properties. But the similarities largely ended there, and the differences were profound and telling. Unlike Oumuamua's enigmatic cigar-like shape and mysterious non-gravitational acceleration without visible outgassing, 3I Atlas behaved exactly like what it appeared to be, a comet. It developed a classic coma and tail structure. Its brightness variations followed predictable patterns based on volatile sublimation. Its trajectory showed the expected gravitational deflection from solar interaction, with additional perturbations easily explained by outgassing forces. Most importantly, 3I Atlas exhibited no signs of controlled or directed motion. Its path through the solar system followed the precise hyperbolic trajectory expected for an unbound visitor under the influence of solar gravity alone. There were no course corrections, no unexplained accelerations, no radio transmissions, and no artificial structures visible. The scientific method demands extraordinary evidence for extraordinary claims, and the evidence for 3I Atlas consistently pointed toward natural phenomena, albeit natural phenomena unlike anything previously observed in our cosmic neighborhood. Every strange behavior, every unusual chemical signature, and every anomalous physical property had plausible explanations rooted in well-established physics and chemistry. The extreme carbon dioxide dominance, while unprecedented in solar system comets, could easily result from formation in the outer regions of an unusual planetary system. Stars with different masses or planetary architectures might naturally produce comets with chemical signatures that seem alien to observers, familiar only with our local solar system's products. The apparent iron depletion relative to nickel could reflect either formation in a stellar environment with non-solar elemental ratios or subsequent processing during billions of years of interstellar travel. The real question was not whether 3I Atlas could be artificial, but why people kept asking. Part of the answer lies in the profound psychological impact of contemplating truly interstellar scales. When we observe objects from other star systems, we confront the possibility that intelligence might exist elsewhere in the galaxy. The human mind naturally looks for signs of purpose or intention in unexplained phenomena. But nature routinely produces phenomena that exceed human imagination. The universe has had 13.8 billion years to experiment with physics and chemistry under extreme conditions. This does not mean we should abandon the search for extraterrestrial technology. But the detection of such civilizations will require clear, unambiguous evidence of artificial origin. Coherent radio signals with information content, objects displaying controlled motion inconsistent with natural forces, or structures that violate the known laws of physics. 3I Atlas displayed none of these characteristics. Perhaps most tellingly, 3I Atlas was behaving exactly like what we would expect from the debris of planetary formation around other stars. An authentic sample of another star system's debris should look alien compared to solar system objects, while still obeying the same fundamental laws of physics and chemistry that govern matter throughout the universe. The fact that it seemed strange to human observers was not evidence of artificial origin, but rather confirmation that we live in a galaxy where conditions for planetary formation vary dramatically from system to system. Tracing the biography of an interstellar visitor requires reconstructing a journey that may have lasted longer than Earth has existed. 3I Atlas carries within its chemistry and trajectory the fossilized record of cosmic events that unfolded billions of years ago. The first clues to the object's ancient origins emerge from kinematic analysis. Preliminary calculations suggest that 3I Atlas may have originated from the galactic thick disk, a population of stars that formed during the Milky Way's early evolution between 7 and 12 billion years ago. If these models prove correct, 3I Atlas would be older than our entire solar system. It would have been wandering through interstellar space since before the Sun condensed from its parent molecular cloud. The thick disk hypothesis gained support from the object's unusual chemistry. Stars in this ancient galactic component typically show different elemental abundance patterns compared to younger populations like our Sun's. The ejection process typically involves gravitational interactions with giant planets during the chaotic early phases of planetary system evolution. Computer simulations suggest that every planetary system ejects vast quantities of debris during its formation. Once ejected, 3I Atlas would have begun a solitary odyssey through the near vacuum of interstellar space. Yet, this interstellar journey was not entirely uneventful. Recent modeling has identified several close encounters with other stellar systems during 3I Atlas's long voyage. Over the past 10 million years alone, the object appears to have passed within approximately 1 parsec, about 3 light-years, of at least half a dozen different stars, each encounter potentially altering its trajectory through subtle gravitational perturbations. The object has maintained structural integrity throughout its billion-year journey, despite being subjected to thermal cycling, cosmic ray bombardment, and occasional impacts with interstellar dust grains. This suggests either unusually robust construction or continual self-repair through sublimation and redeposition processes that gradually heal micrometeorite damage. The object's arrival in our solar system represents the culmination of a journey that defies human comprehension. Consider the navigational precision required for 3I Atlas to arrive at precisely the right time and trajectory for optimal observation by 21st century human telescopes. This timing seems almost too perfect to be coincidental. The biography of 3I Atlas also illuminates the broader story of galactic evolution and the cosmic recycling of planetary materials. Every heavy element in the object's composition was forged in the nuclear furnaces of ancient stars. In a very real sense, 3I Atlas serves as a messenger from the ancient galaxy, carrying samples of planetary formation processes that occurred under conditions dramatically different from those that created Earth. Yet, for all the sophisticated modeling and chemical analysis, fundamental questions about 3I Atlas's origins remain unanswered. We cannot definitively identify its parent star. The gravitational chaos of galactic evolution has erased most traces of its original trajectory, leaving only statistical hints. This uncertainty reflects the inherent challenges of interstellar archaeology. But these limitations do not diminish the significance of what 3I Atlas represents: an authentic sample from another world, formed under conditions different from those in our solar system. The convergence of enhanced detection capabilities, improved deflection technologies, and growing international cooperation sets the stage for multiple possible futures in humanity's relationship with cosmic threats. The September surge and 3I Atlas encounter provide glimpses of what these futures might look like, ranging from triumphant mastery of our cosmic environment to sobering reminders of our continued vulnerability. In the most optimistic scenario, the technological and institutional foundations laid during the 2020s mature into a robust planetary defense ecosystem that effectively eliminates asteroid impact risks. The Vera C. Rubin Observatory's unprecedented survey capabilities, combined with space-based infrared detection from NEO-Surveyor, create comprehensive awareness of incoming objects with decades or centuries of advanced warning. This extended lead time transforms deflection from desperate last-minute interventions into routine celestial traffic management. Gentle nudges applied years in advance divert potentially hazardous objects into safe trajectories using proven kinetic impact techniques. Under this scenario, 3I Atlas emerges intact from its solar encounter and yields unprecedented insights into interstellar chemistry and galactic material exchange processes. The detailed characterization establishes interstellar archaeology as a major scientific discipline. Improved survey systems detect dozens of additional interstellar visitors, each one carrying unique chemical signatures that illuminate different aspects of planetary formation around other stars. This scientific windfall drives technological development in spectroscopy, precision astrometry and coordinated multi-telescope observations. But alternative scenarios present more challenging possibilities. The moderate pathway acknowledges that improved capabilities will inevitably encounter real tests as the catalog of potentially hazardous objects expands. Statistical projections suggest that one or more city-killer-sized objects, 100 to 300 meters, will eventually approach Earth with insufficient warning time for gentle deflection measures. These scenarios would require more aggressive intervention techniques, potentially including nuclear explosive devices that carry significant technical and political risks. Failure could result in regional devastation and fundamental questions about humanity's ability to protect itself from cosmic threats. Ocean impacts present particularly complex challenges. The majority of Earth's surface is covered by water, making ocean impacts statistically more likely than land impacts. But tsunami generation from ocean impacts remains poorly understood. A 200-meter asteroid striking deep ocean could potentially generate 10-meter waves that remain dangerous across entire ocean basins. Coastal cities could face devastating tsunami impacts hours after a mid-ocean collision. The warning time provided by successful detection might be sufficient for evacuation, but the economic and social disruption would be enormous. The worst-case scenarios, while statistically unlikely over human timescales, represent existential challenges that current technology cannot address effectively. A long-period comet from the Oort cloud could arrive with only months or years of advanced warning, carrying enough kinetic energy to threaten human civilization regardless of deflection attempts. These extreme scenarios serve as reminders that planetary defense provides protection against most threats. Not all threats. The goal is not perfect security, an impossible standard, but rather reasonable protection against reasonably likely threats. The economic and political implications are also varied. The commercial space industry's growing involvement in asteroid-related activities introduces market dynamics that could either support or complicate planetary defense efforts. Private companies, motivated by asteroid mining profits, might develop characterization and rendezvous capabilities that serve dual purposes. But commercial priorities do not always align with planetary defense needs. A potentially hazardous asteroid that also contains valuable resources might face competing claims from mining companies and deflection missions. Yet, the cosmic perspective provided by objects like 3I Atlas offers unique opportunities to transcend terrestrial divisions and focus on shared human interests. The knowledge that our planet exists within an active galactic environment, filled with potential threats and opportunities, could catalyze cooperation in ways that purely terrestrial challenges cannot achieve. As we stand at the threshold of potentially revolutionary improvements in our ability to monitor and manage cosmic threats, the futures that emerge will depend as much on our social and political choices as on our technological capabilities. The cosmic choreography of late 2025 was reaching its climax as 3I Atlas approached its date with solar destiny. October 30th marked the calculated perihelion passage, the moment when this ancient wanderer would sweep closest to our sun. This crucial encounter, however, would unfold hidden from human eyes, masked by the overwhelming glare of our nearest star. For astronomers, the perihelion period represented both the most scientifically valuable phase and the most frustrating observational challenge. This was when maximum solar heating would drive the highest levels of volatile sublimation, potentially exposing subsurface materials preserved since the object's formation. But the object's trajectory carried it to within approximately 0.44 astronomical units of the Sun, less than 10 degrees from the solar disk, buried in the twilight glow that makes precision astronomy impossible. The enforced observational hiatus created a tantalizing mystery. Would 3I Atlas survive perihelion intact, emerging in December as a single coherent object with enhanced activity? Or would thermal stresses fracture its internal structure, breaking it apart into multiple fragments? Intact survival would suggest that interstellar objects possess sufficient structural integrity to preserve ancient chemical signatures, even when subjected to intense solar heating. Astronomical patience has its rewards. Earth's orbital motion gradually improves viewing geometry, and by early December, 3I's Atlas would begin emerging from the solar glare into prime observing position. The object's closest approach to Earth was calculated for mid-December, at a distance of approximately 270 million kilometers. This represented optimal conditions for detailed spectroscopic analysis, close enough for major telescopes to collect substantial amounts of light, yet far enough to avoid atmospheric interference. The December observing window would likely represent the best opportunity to study intact interstellar material that human science might encounter for decades or centuries. 3I Atlas's trajectory and timing would keep it within range of major observatories well into 2026, providing months of sustained observation across multiple wavelength ranges. Meanwhile, the enhanced capabilities of the Vera C. Rubin Observatory were ramping up operations. Its enormous mirror and wide-field camera can rescan the entire accessible sky every 3 nights, providing near real-time monitoring of cosmic traffic in our local neighborhood. This enhanced cadence would revolutionize asteroid detection and tracking, potentially revealing that the September surge was not an anomalous clustering, but rather a representative sample of the true activity level in near-Earth space. The space-based component of our detection network was also preparing for major upgrades. NASA's Near-Earth Object Surveyor, scheduled for launch in September 2027, would deploy an infrared telescope specifically optimized for asteroid detection. Operating from a position trailing Earth, NEO Surveyor will be able to detect objects approaching from the sunward direction that remain invisible to ground-based surveys, finally closing the detection gap that allowed the Chelyabinsk impactor to arrive unnoticed. As winter settles across the northern hemisphere and 3I Atlas prepares for its December reemergence from solar glare, we find ourselves at a remarkable inflection point in humanity's relationship with the cosmos. The events of September 2025, from FA-22's close approach to the discovery of our third confirmed interstellar visitor, have given us something far more valuable than scientific data, a new lens through which to view our place in the universe. For most of human history, the night sky appeared static and predictable. This perspective fostered a sense of cosmic isolation. The September surge shattered that illusion. We discovered that our solar system is not a quiet suburban neighborhood, but rather a busy intersection where ancient travelers from distant worlds regularly pass through, carrying messages from their origins. 3I's Atlas alone represents a direct physical connection to stellar processes that occurred billions of years ago in regions of the galaxy we may never visit with spacecraft. This constitutes a fundamental shift in cosmic perspective. We are not isolated products of a single stellar system, but participants in galactic-scale processes that have been exchanging materials and information between worlds for longer than Earth has existed. The chemical signatures preserved in 3I Atlas's ancient materials carry information about stellar nucleosynthesis rates, planetary formation conditions, and volatile chemistry in environments that existed before our sun began to shine. Perhaps most importantly, the September events have demonstrated that we now possess the technological capability to recognize, study, and potentially interact with this galactic-scale system of material exchange. The same detection networks that tracked FA-22's approach and will monitor Apophyse's 2029 flyby can also identify and characterize interstellar visitors like 3I Atlas with sufficient precision to extract detailed scientific information. We have graduated from passive observers of cosmic phenomena to active participants in interstellar archaeology. This transition carries profound implications that extend far beyond astronomy and planetary defense. The infrastructure required for monitoring cosmic threats and studying interstellar visitors provides templates for addressing other global challenges that transcend national boundaries, such as climate change and pandemic response. The lessons learned from tracking asteroids and characterizing comets could prove equally valuable for monitoring greenhouse gas concentrations or managing shared resources. More fundamentally, the cosmic perspective fostered by awareness of interstellar visitors like 3I Atlas offers an antidote to the parochial thinking that often hampers cooperation on global issues. When we recognize that Earth exists within a dynamic galactic ecosystem, terrestrial divisions based on nationality or ideology begin to seem less significant. We are all passengers on the same small planet, threading its way through a galaxy filled with ancient debris from billions of other worlds. The September surge has also highlighted how much we still do not know. Current models predict that interstellar visitors should be relatively rare. But if 3I Atlas represents typical rather than exceptional activity levels, our estimates might be off by orders of magnitude. The Vera C. Rubin Observatory and other next-generation survey systems could reveal that dozens or hundreds of interstellar objects pass through our solar system annually. This would transform our understanding of galactic material exchange rates and the frequency of information transfer between stellar systems. As 3I Atlas prepares to re-emerge from behind the solar glare, carrying chemical signatures from another star system and another era of galactic evolution, we stand ready to receive its messages. What we learn from this ancient wanderer may reshape our understanding of how worlds form around other stars, how life-essential materials get distributed throughout the galaxy, and what it truly means to be cosmic citizens in a universe where 400 billion stars are constantly exchanging their most precious substances across the vast distances of interstellar space. Do not let the cosmic mystery of 3I Atlas vanish back into the void. The coming decades promise a revolution in our understanding of interstellar life, galactic history, and humanity's place among the stars. To stay at the forefront of this journey and receive the most detailed analysis of every cosmic anomaly, subscribe to Stellify Science now. Hit the notification bell and commit to exploring the universe with us. Your cosmic education is just beginning.